In our earlier videos, we looked at alkenes and their addition reactions. That was video number 321, where we did a general overview of addition reactions, looking at hydrohalogenation, looking at hydration, and looking at hydrogenation. Then we transitioned from there to looking at the mechanism for how these reactions take place, exploring the hydrohalogenation in detail to look at each electron transfer step to go from reactant to product. For all of those prior examples, we were looking at symmetrical alkenes, where each of the two carbon atoms of the alkene group had the same number of alkyl groups bonded to it, or alkyl substituents. Now what we're going to do is instead transition to looking at asymmetric alkenes. The challenge with asymmetric alkenes, where we have a carbon-carbon double bond that on one side has one alkyl group bonded, on the other side has two, such as the two methyl groups here, whatever you want to fill in here. For this asymmetric scenario, there are two possible reaction products that are constitutional isomers of one another. One of those constitutional isomers corresponds to attaching atom Y, whatever atom Y is, at carbon number 2 of the chain, and then X at carbon 3 of the chain as we go down the longest carbon chain. The other would correspond to the constitutional isomer where we flip-flop which carbon atom X bonds to relative to which carbon atom Y bonds to. If we counted here, we'd go to position 1. Position 2 is where X is bonded, versus over here it was atom number Y was at position number 2. So how do we decide which of these two products is going to be the real deal? Which one is actually the constitutional isomer that is observed as the product of these reactions? By the end of this video, you'll be comfortable evaluating hydration reactions where we're adding water across the carbon-carbon double bond, as well as hydrohalogenation reactions where we're adding HCl or HBr to predict what the product would be resulting from adding X and Y across the carbon-carbon double bond. To evaluate what product we would expect from these reactions, we apply what's referred to as Markovnikov's rule. Markovnikov's rule will tell us what constitutional isomer will result from the addition of HX, meaning HCl or HBr, or water plus acid to a carbon-carbon double bond. And what's going to happen in Markovnikov's rule is that with Markovnikov's rule, we are going to add H to the carbon that has more direct bonds to hydrogens, and we are going to add the other group, such as the halogen or the OH group, to the carbon with fewer direct bonds to hydrogen. So the rule here is that when adding HX or water, H adds to the carbon of the alkene group that has more hydrogens directly bonded to it, whereas X for our halogen, or OH if we're doing a hydration reaction, adds to the carbon of the carbon-carbon double bond that has fewer hydrogen atoms. So this rule, when we apply it, will allow us to predict which of the two carbon atoms of the carbon-carbon double bond is going to pick up a hydrogen in these addition reactions, and which one is going to instead pick up X or OH, where X is our halogen atom. Let's look at this as applied toward a problem. So taking a look at structure here, we'll draw it out as a condensed structural formula. You could also draw it as a line angle formula if you wanted as well. We're going to draw an asymmetrical alkene. We'll react with HCl. And in this addition reaction, we are going to anticipate that the HCl will add across the carbon-carbon double bond, where one of the two carbon atoms will get H and the other one will get Cl. We need to figure out which carbon of these two is going to pick up H and which is going to pick up Cl. We use Markovnikov's rule to establish that, where Markovnikov did a series of experiments and empirically determined that this was the case way, way back when. And since that time, the reaction mechanism for this reaction we could actually use to predict the stability of the intermediates and guide us toward the correct product here. But we'll follow Markovnikov's rule rather than trying to go through the full mechanism for this. And what's going to happen here is that looking at the two carbon atoms to predict the product, we would say that this carbon is the carbon that has less hydrogens directly bonded to it, because this particular carbon atom has no hydrogen atoms directly bonded to it. The hydrogens here and here instead are directly bonded to this carbon to fill its octet. So that has fewer hydrogens, whereas we come over to here, and this carbon is the one as we would describe as having more hydrogens directly bonded to it because it has this one hydrogen directly bonded to it here. So that's a larger number than the 0 that we see bonded over here. So therefore, since that has more hydrogen atoms directly bonded to it, that's going to be the location where H is going to bond from HCl. On the other hand, the carbon that has fewer hydrogens per Markovnikov's rule is going to be the location where our halogen, our Cl, will bond. So we can go ahead and fill in, based on our understanding of addition reactions, that we're going to add across that carbon-carbon double bond. We need to fill in H on one side and Cl on the other. And our Cl is going to go on the carbon that has fewer H's directly bonded to it. That's here on the left, corresponding to this one right here. And then on the right, the blue circled carbon, which corresponds to the one over here, is going to be the one that picks up H, because that was the carbon that had more H's directly bonded to it at the start, because it had this direct carbon-hydrogen bond here, and that causes it to be the winner. So our final product would correspond to this constitutional isomer, rather than what was the other hypothetical possibility where the H and the Cl were flip-flopped. Instead, there is a specificity for making this particular constitutional isomer following Markovnikov's rule. We can apply this as well toward a situation where we do a hydration reaction. Hydration was where we were adding water across the carbon-carbon double bond. And we could look at an example here. And I'll use a line angle formula to illustrate another way that you might see these structures come into your life. And in the case of this, it can look like so. And I'm going to plug in above the arrow H2O and H2SO4, which is sulfuric acid. Acid acts as a catalyst of this reaction. And what we'll add across the carbon-carbon double bond when we look at adding water is it's always going to add H to one of the carbons and OH to the other carbon. And following Markovnikov's rule, what we do is we look at the two carbons of the alkene here and here, and we say which one of those has fewer hydrogens directly attached and which has more. So the one on the left has fewer hydrogens directly attached. In fact, at this carbon, we have no hydrogens directly attached because to get the complete octet, we have a methyl group here, and a carbon-carbon double bond. The carbon on the right has more hydrogens directly attached. It has one hydrogen directly attached, which has to be here to fill the complete octet on this carbon. And so following Markovnikov's rule, the carbon atom that has more hydrogens to start with is going to be the one that will gain the hydrogen from water. On the other hand, the carbon that has fewer hydrogens is going to be the one that gains the other group, in this case the OH group. And so drawing out the product that we would expect of this reaction, I'm drawing out the skeleton of the molecule the same as before in terms of the carbon atoms and how those are connected. So I drew out the basic skeleton of this molecule exactly like it was here, over here, and then keeping in mind where the double bond was, wherever the double bond was is where we're going to plug in OH. So the OH is bonded to this carbon, and the H is bonded right here. And in actuality, due to the fact that this is a line angle formula that we are showing here, it's implied that this hydrogen that we have shown in green right here is actually there. So you could have also been completely accurate if you had drawn this structure out without that hydrogen explicitly shown. As long as you're not showing a formal charge there or anything like that, it's implied that that's a CH2 group, meaning that this CH group that we started with the alkene has picked up a hydrogen to become CH2, giving us our final product of our hydration reaction following Markovnikov's rule. And Markovnikov's rule, to recap, will always apply toward hydration reactions where we're adding water across the carbon-carbon double bond, and hydrohalogenation reactions where we're adding HCl or HBr. And you'll use this anytime you're working with an asymmetrical alkene, where rather than having the same number of hydrogens attached at each of the two carbons, instead one of them has more hydrogen atoms and one has fewer, making the structure of the alkene asymmetrical.